I'm sure there is a reason, but it's certainly beyond my scope of understanding at this point.
So you just always use.
It's always done with odd, and these are called harmonics. They're whole number multiples of the same frequency, the fundamental frequency. This is what we call the fundamental frequency. This is the third harmonic. This is the fifth harmonic. This is the 7th, 9th, 11th, 13th. Any multiple of the waveform's frequency is called a harmonic.
Okay.
Okay, if you were listening to that in terms of music, you're looking at octaves. So if I play an A on the piano and I play the A twice up an octave, that's going to be twice the frequency.
Okay.
If I go up another octave, it's going to be twice that frequency.
Okay.
Okay, so the even harmonics basically double things. When you jump into the odd harmonics, it does some phasing things and throws things out of whack just enough as to where the waveforms add together properly. So when you look at what you're actually getting, let's go ahead and sort of try. I'm no artist, but let's go ahead and see if we can kind of draw a picture of what this is going to look like. We're going to take a 1 kilohertz sine wave. We're going to add to that what? A 3 kilohertz sine wave is about 1/3 of the amplitude, which is going to give us something like this. We're going to add to that a 5 kilohertz. We're going to add to that a 7 kilohertz, which is going to ride up on that. And I think you can see as we start to add more of these together, what's it starting to look like?
A mess.
It's starting to look like a mess because I'm a crappy artist. But you can also see that we're starting to get a square pattern out of that when we add all those waveforms together. And that's what we're actually going to get when we add all of these together. Okay? In the frequency domain, it's really simple to see this. If I pump the square wave into a spectrum analyzer, what I'm going to get is I'm going to get something like this. Here's my amplitude, here's my frequency, here's 1 kilohertz, here's 3 kilohertz, and it's about 1/3 of that. Here's 5 kilohertz, it's about 1/3 of that, or 1/5. 7 kilohertz, and we'll get littler ones all the way up basically to infinity.
You're more or less layering them.
That's right, we're just layering them. Remember that we talked about superposition?
That explains the third of them. It's geometric. You're making a cube instead of a square.
That's right, you're making a cube instead of a square. That's kind of what you're actually doing there. And we talked about the fact that there was a kind of a z-axis that, you know, if you get your head wrapped around that, that's great. If you can't get your head wrapped around it, it's no real big deal either, because typically as a technician, you're going to be making measurements. You're probably not going to ever have to design anything like this, but you may have to measure a square wave and see what its components are. It's very similar to the way colors work. Colors are what? What are colors actually?
Colors are from the spectrum of light.
In the spectrum, right? Spectrum analysis works with light also, because colors are just frequencies.
Yeah.
The only difference between red and green is what frequencies they are. Okay, so we're talking about audio here, and really in a sense, in terms of waveforms, there's very little difference between audio, radio, video, and light. It's all a combination of different frequencies put together. The net result is what you see or what you hear. Okay? Computer monitors use basically what? 3 colors?
Yeah.
Red, green, and blue. And they can make, out of those 3 colors, they can make what? I think 24 million colors easily. And that's just based on how much memory you're using. So really, when we talk about waveforms and colors and frequencies and everything else, we're talking about taking the same thing, different frequencies, adding them together to make something different. That's probably the easiest way to explain it. So now when we look at this, we can see from this what the spectrum or the bandwidth of that signal is. And that becomes very important to us when we start talking about filtering. Okay? I'd like to put up one more waveform and show you one more example of a typical waveform that is not a sine wave and what it is made of. Okay? And then we're going to start talking about filtering. Because we're just getting ourselves to the point where we can now talk responsibly about filtering, because we need to be able to see what our frequencies look like, because what does filtering filter out? Frequencies, right? So we need to know what frequencies we're dealing with before we can possibly even entertain the thought of looking at what happens when we start to remove them. So let's look at the next waveform. Is there any questions on this one first? All right, let's look at one more type of waveform here. And I'm going to leave some of this stuff the same because it's going to be the same frequencies, just different values. Let's look at a triangle waveform with an amplitude of A. For the triangle waveform, we're going to change this 3 to a 9. We're going to change that 5 to a 25. What do we do? What did we do mathematically to our previous waveform?
Well, that goes up by 3, and that goes up by 5, so.
Divide by square.
We divide by the square of the harmonic number instead of just dividing by the harmonic number. Which means now, if we want to look at our triangle waveform, let me get rid of a piece of that. We're going to see something like this. Okay, 1 kilohertz. At 3K, we're going to see something even smaller. We're going to see A over 9. Here, we're going to see A over 25. Here, we're going to see what? A over 49. So look at what happened to our spectrum. The harmonics are smaller. And I guess, really, doesn't that make sense? Which looks more like a sine wave, this or a square wave? That looks a little bit closer to this than this does, doesn't it?
Correct.
Okay, so it's like a recipe, folks. I can add 1 tablespoon of 1 kilohertz, 1/9 of a tablespoon of 3 kilohertz, 1/25 of a tablespoon of 5 kilohertz. Add that all together and mix it up. Guess what? You got this. If I take a sine wave, 1 kilohertz, 1 tablespoon, 1/3 of a tablespoon of 3 kilohertz, 1/5 of a tablespoon of 5 kilohertz, add it all together, I'm going to get this. And indeed, if I were to be recording what I'm doing right now, which in fact I am, and I was to take the audio out of that, every bit of that audio can be broken down into a combination of sine waves. Okay? Questions? Is this making any sense? It's a lot of theory, not much practice. What's that?
1 over time formula. I have half of it in my head. I still can't figure it out.
What's that?
I know it's 1/time, but when you're doing the 3K to get to 1 milli, I don't know how to keep
No, we
calculate
didn't
it.
do 3K to get 1 milli, we did 1K to get 1 milli.
Oh, 1K to get 1 milli.
Yeah, 1K to get 1 milli.
That explains it.
3K would be 333 micro.
Okay, that's what I was getting.
Yeah.
Frequency is 1 at a time.
So it's always a reciprocal. You can do that over and over again. Take the reciprocal of the period, you get the frequency, and every time you do it, you should keep getting the same two numbers,
Alright.
right?
Landon,
Yeah.
when you're talking about splitting these frequencies up, that's essentially what those super large mixer boards you see in like the music industry.
Sure, in a sense, that's what mixers do. If I was able to take if I were to take all of these frequencies and put them into a separate channel of a mixer board and set my mixer knobs to look like this, and I look at the output on a scope, I'm gonna get a square wave, I'm gonna get a triangle wave.
I'm probably gonna get out of the subject because but asking a question. If this is the way they break down when you take a recording and separate the voice and the music.
Well, that's a little bit of a different thing because a lot of times if you and I are singing together in a choir at church, our voices are about the same frequency.
Yeah.
So it's gonna be hard to pull one person's voice out of that.
When it comes to instruments, and then it'll be a little different.
Yeah, it would be a little bit different, but really, we're looking at individual sine waves making up a total. You're not gonna be able to pick out a trumpet out of that because a trumpet is not a pure sine wave. A trumpet waveform looks like a sawtooth,
Okay.
right? A flute waveform looks more like a sine wave. A clarinet waveform looks similar to a sine wave. A violin waveform looks like a sine wave that looks like that. So, you know, you can't pick the instruments out because they all have their own waveforms as well.
Okay, so it makes sense what I said, and then they could pick it out of the instrument, but out of the voice is totally different.
Right, exactly. You can pick out what sine waves went in to make that instrument or that voice sound. The main one, the largest of those sine waves will be whatever frequency you happen to be playing. If you have an oboe and you're playing an A, then you're gonna see 440 hertz as your main primary or fundamental frequency. What actually gives it its tone, however, makes it sound different from other instruments, is what we've got going on up here, okay? These two things will sound completely differently if you actually listen to them.
Yeah.
And you can break them down through what they call Fourier analysis and pull out all of the individual ingredients to it. Just like if you ever watch CSI, where they'll take a piece of hair or a piece of blood and they'll be able to figure out what's in it, or a piece of any kind of material, they can basically burn it and figure out what all the elements are that made it up. All material is made up of elements. All waveforms are made up similarly of sine waves. Different frequencies added together to make a whole. Right? Does that make sense? Okay, this is where filtering becomes important now. All right, let's look at this, and I'm going to go ahead and get rid of everything on the left-hand side of the board if there are no objections, and move on to talk about what filtering does for us. And we're going to revisit a couple of the things that we talked about last time we all got together. I didn't imagine at that time that we would end up revisiting that, but do you remember we talked about how you were lied to in first term about wire? Remember that discussion? That's going to become important today. Surprisingly enough, I happen to be able to come back in and teach you guys when I get to show you the rest of that story. So that's kind of cool. All right. I won't put that in front of you.
Okay.
I do. Okay. Here is our, what is this called? Spectrum analysis of a square wave. Right? Let's filter it. And we're going to filter it with a low pass filter. What does a low pass filter do?